Chapter 18, Electrochemistry. Let's check out number 1. For the reaction of sodium bromide and chlorine gas to form sodium chloride and bromine. Okay, I know we're going to need a balanced equation here. So let's do sodium bromide and chlorine gas. Sodium bromide and chlorine gas yields what? Sodium chloride and bromine. Sodium chloride and bromine. That's a liquid. It doesn't say that, but I know it is. Okay. What they're asking us to do is to break this down into half reactions and show the proper half reactions that would be expressions for this equation, oxidation reduction. Actually, we can balance this one with the budget method. All we have to do is say with 2 bromines there, we need 2 here. 2 chlorines there, we need 2 here. And that gives us 2 sodiums. So we're good. Okay, now we need to assess their oxidation states. Right? These elements, of course, are 0. This is a -1 because it's a, well, actually, this is a +1 because it's an alkali metal. That makes this one a -1. Similarly here, there. Okay, so the oxidation step, let's see, that's the way they have it in order. Oxidation first and reduction second. Okay, so the oxidation is going to be, oxidation is loss. Who lost electrons? Well, sodium went from plus, well, actually, sodium is a spectator, isn't it? Because it didn't change. Bromine went from a minus to a 0, so it had to lose electrons. It would come down here. So we might as well do that one right now. And the answers tell us that they're not particular about the phase, so we won't worry about that. So that's a minus. And that leads to Br2. And since we have a 2 prefix here, it propagates through the entire compound. So that means we have 2 Br minuses. Well, if it, oh, excuse me. No, that's not right. This is oxidation. Right? It had to lose electrons to go to 0. So how many electrons? Well, 1 electron per bromine, but there are 2 bromines, so that's 2 electrons is required to be lost. Okay, so obviously now chlorine had to gain 2 electrons to yield Cl minus, and there are 2 of those. Okay. All right. So oxidation first. 2 Br minuses, 2 electrons, and a bromine. 2 Br minuses, 2 electrons, bromine. B, yeah. B looks like it's the best. So let's check the reduction to be sure it's true. Right. Reduction would be 2 chlorines plus 2 electrons yields 2 Cl minus. That means B is our best answer here. I just got off on the wrong foot. All right, number 2. Ammonium metavanadate reacts with sulfur dioxide in acidic solution as follows. The ratio of X to Y. All right, let's see. We're starting off with the vanadate ion with some coefficient. and then SO2, this coefficient, and then VO2 plus, and SO4 2 minus. First clue is that this problem is telling you that these coefficients are going to be the same, and these are going to be the same. What we want to know is the ratio of the X to Y. Okay. It might be possible to do this with the budget method. Let's see. We got 5 oxygens here and 5 oxygens there. Yep. Got 1 V here, 1 S there, 1 V there, it's there. No, that's not going to work. Okay, so we're going to have to do this with the method of half reactions. All right. So if this is a -2, then we have -6 total, but we want to hold one of them out. So that's -5 here. This is a +5. This is a -2 times 2 is a -4. This is a +4. And this side we have -2. There's only one of them. And we need to get a 2 plus out of that. So how do you get a 2 plus? Well, if we have a +2 over here, that brings it to 0. So we need 2 more. So that's a +4 to give us a 2 plus. And this side we have a -2 times 8 is a -2 times 4 is -8. Hold 2 of them out. -6 means a +6 here. So we got our we have our oxidation states. Now we need to separate them out. Okay, so reduction. Which one's reduced? We've had to add electrons. We go from +5 to +4 means this species, +5, we had to add electrons. Oops. All right. 2 plus. And this is a +4 for that vanadium. Okay, that means we have SO2 here with a +4, and that goes to SO4 2 minus with a +6. Okay, balance the oxygens. 3 on this side and 2, and 1 on this side. We need 2 more on this side. Right? 2 oxygens to balance the oxygens. Now we have 4 hydrogens that have to be balanced on this side. We have 2 oxygens here and 4 there. That means we need 2 more oxygens on this side. Now we need 4 hydrogens on this side. Now we can do the electrons. If we go from +5 to +4, that means we had to add 1 electron here for the vanadiums. Okay, I skipped a step because the non-oxygen, non-hydrogens are equal. I didn't even bother with it. 1 sulfur, 1 sulfur, 1 vanadium, 1 vanadium. Now we're back to electrons. On this side, we go from +4 to a +6. That means we had to lose 2 electrons for each sulfur. Okay? All right. So we balance the electrons. We multiply this one by 2, and that gives us 2, 8, 2, 2, and 4. Okay. Now, do we really have to bring everything down? We might be able to do it without bringing everything down if we just want to know that ratio between these two. Right? So we can say there are 4 waters over there, 2 over here. Those 2 go away, and that leaves us back with 2. The electrons go away. Hydrogens, 4 there. We're back to 4 here. Right? And we bring it down. We have 2 vanadiums. We have 1 sulfur dioxide, and we have 2 vanadium here and 1 sulfur dioxide. So the ratio of X to Y is equal 2 to 1. Okay? Now, if you feel more comfortable, you can go ahead and bring everything down and go through the procedure. That's perfectly all right. But we got the answer. Okay, let's see. I think 3 is also on the agenda. There it is. Let's see. In a balanced equation, the coefficient of water is. Okay, so this one we have to also do with a half reaction method. We've got the nitrate, polyatomic ion, we've got the iodide, ion yields iodate and nitrogen dioxide. So that one's -1. This one is -2 times 3 is -6. Hold 1 out. So this is a +5. Right? -2 times 3 is -6. Hold 1 out, -5. This is a +5. And -2 times 2 is -4. So this is a +4. Okay, we got our oxidation states. Now we separate out our half reactions. All right. Which one received electrons? We added electrons to nitrogen. To go from a +5 to a +4, we added 1 electron. So that means NO3 minus here. And I'll keep the oxidation state for clarity. And NO2 +4 there. Okay, that leaves iodide ion, and iodate ion. This is +5, and that's a -1. Okay, so now we want to balance the non-hydrogen, non-oxygens. Nitrogen's balanced, iodine's balanced. We go next to oxygens. We need 1 more on this side. That means we have 2 hydrogens on this side. Okay, we have 3 oxygens there. So that's 3 waters and 6 hydrogens over here. Okay, now we can do the electrons. We added 1 electron for each nitrogen. Okay, and for this one, how many electrons did we lose? Well, you lose 1 to go to 0 and lose 5 more to go to +5. So that's 6 electrons lost. Okay, so now to balance everything out, the electrons, we just need a multiplier of 6. So that means 6 here, 12 there, 6 there, 6 there, and 6 there. Okay, and the question is, what's the coefficient for water? Well, let's see, we've got water here. We also have water here. Right? We have 3 on this side. Take away 3 from here. The coefficient for water is 3. Okay? We don't have to bring everything down because that answers the question. Save you time. All right, number 4. Let's see. The following a reaction in basic solution. Okay. 2O and O2 and F minus. The sum of the coefficients. Okay. So first of all, this oxidation state 0 there, 0 here, -1 there, -2, and +1 there. Okay. So what happened to each one? Well, let's see. Fluorine went from 0 to -1, so it was reduced. Okay. That leaves oxygen, right? Hydrogen is a spectator. In fact, hydrogen's only on this side. We'll have to deal with that in a minute. That's 0. It went from -2 to 0, which means it was oxidized. Okay. We have 2 fluorines here. We need 2 there. We have 1 oxygen here. We need 2 oxygens. Now we need 4 hydrogens. And on this one, we don't have oxygens or hydrogens. It's good the way it is. Now we can go to electrons. So to go from 0 to -1, we had to add an electron for each fluorine, but there are 2 of them. And for this one, we went from -2 to 0, which means we had to lose 2 electrons for each. 2 electrons for each, but there are 2 of them. So that means 4 electrons. Okay? So now this one, we need multiply by 2. That gives us 2 here, 4 there, and 4 there. Now we have the electrons balanced. Okay? Electrons go away. And I'm going to bring this one down. Since we have to convert this to a basic environment, let's bring everything down first. And 2 water, 1 oxygen, 4 fluorides, 4 hydrogens. Okay? So now we can neutralize the hydrogens with hydroxides. And that side, that makes 4 waters on this side and 2 waters on this side. So these 2 go away, and that leaves us with 2. Now we're in basic solution, and those have been converted to waters. So the summation is 2, 4, 1, 4, and 2. So that's 6, 10, 13. 13 is the total of coefficients. All right, next page. Yep. Let's see, we're going to skip a couple, move down to 7. For this redox reaction, which of the following are the correct half reactions? Okay, it looks like it's balanced. Well, let's write it up here and check it out just to be sure. And then A plus 2Cl minus. Okay. Half reactions are going to have electrons in them, so we need to know how the electrons are moving. If this is balanced, then we should be able to do tie lines. I think I've used tie lines before, but we're going to use them this way. Just say space. Right, if we go this iron to this iron, it went from a +2 to a +3, which means it had to lose one electron. So this is the oxidation step. So we had a loss of one electron per iron, but we have two irons, which is 2 electrons. Then if we go from chlorine here to here, this has to be reduction. It gained 1 electron for each chlorine. Times 2 chlorines equals 2 electrons. Okay, so the electrons balance. And the half reaction, let's see, which is the following correct half reactions. Okay, the first one has chlorine in it. All right, so we start off with Cl2. That would be either 1 or 3. And we had to gain 2 electrons. So this would be Cl2 plus 2 electrons yields 2 Cl minus. Okay, that would be number 1, right? Number 1. Roman numeral 1. The second one is Fe2 plus yields 2 Fe3, and that is plus 2 electrons. Okay. And this would be oh, okay. This was a trick question. 2, 2, and 2. If we simplify this reaction, we make that 1, 1, and 1. So that's why Roman numeral 4 is the best one for this one. Okay, so 1 and 4 means A would be your best answer. Okay, number 8. How many electrons are transferred in the following reaction? Okay, let's see. It looks like this one's balanced. Let's do 2ClO3 minus plus 12 hydrogens plus 10 iodide ions, 5 iodine, Cl2, and 6 waters. Let's see. 10, 10, yep. 12 hydrogens, yep. 6 oxygens, yep. And 2 chlorines, okay. So let's see how the electrons work out. This is a -1, this is a 0, that's a 0. Hydrogens and oxygens are spectators. So this would be -2, -6, -5, be +5. Okay, so let's see what happens to the chlorines. How do we go from a +5 to a 0? We reduce it. We add electrons. We gain how many electrons? Go from +5 to 0, we gain 5 electrons per chlorine. But there are 2 chlorines. Times 2 equals 10 electrons. If we go from this one, right, -1 to 0 means we lost 1 electron per iodine times 10 iodines, which is equal to 10 electrons. Okay. So to answer the question, how many electrons are transferred? 10. 10 moles, or we can look at this equation two different ways. 10 electrons for each of these individual atoms and molecules, or 10 moles if we use molar ratios. But the answer is 10. And that's information that you'll need if you want to calculate the actual electromotive force or voltage for a cell, for a galvanic cell. If you're using the Nernst equation, you'll need to know that value. Okay, we'll skip a few and go down to number 11. Let's see, we've got a galvanic cell based on this reaction. Fe2 plus, and then dichromate ion, right? Yields Fe3 plus Cr3 plus. In acidic solution, what's the voltage of the standard cell carrying out this reaction? Okay. If we're talking standard cell, then all we need to know is what's being reduced and what's being oxidized. So if we go from Fe2 plus to Fe3 plus, that's oxidation. All right, so Fe2 plus to Fe3 plus, and then the reduction is Cr2O7 minus, and this is, let's see, -2, -14, -12. This is +6. Oops, I shouldn't have done that. Cr2O7 minus. And this is the reduction, so that means Cr3 plus, we had to add electrons to either side. Now, as far as the standard values go, all we need to do is look up in our table the standard values for each one. This one's going to be a reduction. This one's going to be oxidation, so we're looking for this one to be reduced in our table. Okay, so let's scroll down to our table, see how quick I can get there. Let's see, here we go. So we're looking for Fe3 plus and dichromate. So let me see, Fe3 plus dichromate. There's dichromate with 6 electrons. Yeah, because there are 2. So this is going to be 2, and this is going to be 6 electrons. So that's our first one. So if I'm a place again, that's 1.33 volts. Okay, now we're looking for Fe3 plus to Fe2 plus. And this is going to have, well, 1 electron for each one. But remember, under standard conditions, that's not an issue right now. So let me find Fe2 plus to Fe3 plus to Fe2 plus. Fe3 plus. Here it is right there. Right there. 0.77. And normally what you would do is just say which one needs to be flipped in order to make a positive. But we're already told that this one has to be flipped. It's the oxidation step. So that makes this one negative. And that then we just add them together. 7 from 13 is 6. And 7 from 12 is 5. 0.56 volts. All right, so let's go back up to number 11. Oops, too fast. Number 11, positive 0.56 volts is D. Okay, that's standard value. If we were actually going to calculate, then we'd need concentrations of each of these values to give us, to calculate Q. And then we'd also need to know the number of moles of electrons transferred. But these are standard values, so we don't have to concern ourselves with those issues right now. All right. Let's see, who's next? 14. A strip of copper is placed in 1 molar solution of copper nitrate and a strip of silver in silver nitrate. 2 metal strips are connected to a voltmeter and a salt bridge. Standard reduction potentials are given here. Okay, which of the following statements is false? Okay, we need to know which one is the cathode and which one's the anode. Cathode is the site of reduction. It's going to be on the right. Right? So we need the salt bridge. I'm going to do this rather than draw out the diagram. I'm going to do this with our line notation. Right? So the one that is reduced, let's do the one that's oxidized because that's the one we have to flip. So which one has to be flipped? The copper. Right? Copper, if we make copper negative, then we still get a positive voltage. So that means copper goes on this side. We need the copper solid here. Then we need copper in solution. Okay. And on this side, we need silver in solution. And we need the silver electrode here because we're connecting them like this. And electrons are flowing this direction. Okay. Which of the following statements is false? Well, let's see. Electrons flow in external circuit from the copper electrode to the silver electrode. A is true. How about B? The silver electrode increases in mass as the cell operates. Yes, because you're reducing silver ions to silver. They're being deposited on the electrode. That mass increases. That's true. There's a net general movement of silver ions through the salt bridge to the copper half cell. No, you're not moving the silver ions through the salt bridge because it's being reduced to silver. You're removing positive ions from this side, so positive ions are moving through the salt bridge to replace those. And since we're removing, we're adding positives to this side, then the negative electron, the negative ions that are in the salt bridge move in to replace those missing electrons. Okay, so this is false. That's our false one. The other two should be true. Negative ions pass through the salt bridge from the silver half cell to the copper half cell. True. To replace them with the electrons that are lost, the negative charges. And E, some positive copper ions pass through the salt bridge from the copper half cell to the silver half cell. More than likely, because you're trying to replace silver ions. So the copper, you will have probably something like potassium chloride in the salt bridge. So initially the potassium is replacing the missing silver ions. But eventually, if enough time passes, then some of those copper ions are going to also migrate. We didn't cover that in class, but it is true. Okay. Takes care of that one. Let's see, 15. Okay. 15. Which of the following species cannot function as an oxidizing agent? In other words, if we're looking for an oxidizing agent, it must be reduced. So which one cannot be reduced? That's the question. Okay, we have these possibilities. Sulfur, nitrate, dichromate, iodide, ion, and manganate ion. So which one cannot be reduced? That means it will not serve as an oxidizing agent. Okay. So this one starts off as 0. Can it be reduced? Well, yeah. If we add 2 electrons, then we'll go to, right, which is typical for sulfur. And so that's not a good answer. This is -5 plus 5, right? Can we add electrons to that one? And, well, let's see. Oh, yeah. If we add electrons to nitrogen, right, we could go, nitrogen can have oxidation states of +5, +4, +3, +1, +2, +1. I already said +1. 0, -1, -2, -3. You can have all those. So those are both candidates for reduction. This one is, we did this one before, this is +6, so we can add electrons to that one also, right? We did it before. We went from chromium 6 plus to chromium 3 plus. Iodine. Can we add electrons to iodide ion? No, it's full, right? Those electrons complete the octet for iodine. It doesn't want any more electrons. So this is the one that's the culprit. And if we went ahead and did this one, -2, +7, right? It can take electrons easily. So D is the one that will not serve as an oxidizing agent. All right. Excuse me, 16. Number 16, not the answer. Which metal, aluminum or nickel, could reduce zinc 2 plus to zinc if placed in a ZN2 solution? Okay, which metal would serve as a reducing agent? So if we have, let's see, let's do this. This makes zinc metal. And let's see, aluminum 3 plus makes aluminum metal. And then nickel 2 plus yields nickel. Okay. The question is, which metal, aluminum or nickel, could reduce zinc 2 plus, to zinc if placed in a zinc 2 plus solution? So this one is going to be the cathode, right? Which one of these is able to reduce it? All right, let's do the standard potentials here. -0.76, -1.66 volts, and -0.23 volts. Okay. If this is going to be the cathode, these have to be anodes. So we would reverse our direction. and change the sign. So which one of these added to this one is going to give us a positive value? That would be a spontaneous reaction. Well, not this one, that's still negative. But this one added to that one gives us a positive. So aluminum, let's see. Yeah, aluminum would readily go that direction in a zinc solution to reduce that zinc metal. So aluminum is the only one of those two that would work. Okay. All right, I'm going to have to, I don't want to shrink this picture, so let's assess the problem and then look at the information that's given. Let's see, number 17. All right, we have this galvanic cell. Each half reaction shown below, the contents of the half cells are written beneath each. Okay, so we actually have concentrations given here. Standard reduction potentials are as follows. Okay. What is E0 for this cell? This is very simple. All we have to do is, even if the cell is written backwards, right? We expect the cathode to be on the right side, the anode to be on the left side, but suppose somebody messed up. It doesn't matter. If we look at the values, the standard potentials for each one, then we can assess which one needs to be flipped in order to give us a positive value, right? If we flip the bromine, we get all negatives. If we flip the chromium, right, then we get positive values. And in this case, somebody did write this one wrong. Chromium should be on the left side. It should be the anode because we flipped it. We made it an oxidation. So the values are 0.726, 727, right? For the chromium anode. And for the cathode, it's the value as given. Bromine is on the right-hand side, 1090, 1.090. So that's 1.817 volts. Right, that should be A. Yep, that's A. Now, I'm wondering, no, that's a different one. Let me take a quick look and see if we need to hang on to this one, if it's going to recur at some point. And we might want to skip ahead. No, nothing there. Nothing there. Okay, I can erase this one. And we'll talk about a different cell in number 18. Okay, so we're given another galvanic cell with chromium on the right and manganese on the left. Notice we have a platinum electrode. That means the oxidation reduction reaction is in solution. And the platinum serves simply as to gather electrons to send them through to the other side. Okay, the question here is what's the value of E0? All right. Well, in this case, we look at those standard potentials, and we find that if we flip the chromium to an oxidation, then we get a positive value. That means this cell is written backwards. Right? Chromium should be on the left-hand side because it is the anode. So the anode is going to be minus 1.330. Let's see, this is, did I say this was 18? The anode then is negative 1.330 volts, correct? Yeah. We have to flip the chromium. And then the manganese is going to be 1.506 at the cathode. Yep. Okay, so that's 6, 7, 1. 0.176 volts is E0. So that should be C. Yeah, C. I think this one might be, we might use this one again. Let's scroll down and see. Yeah, there it is again. 506. Then now the question for that same cell is, when current is allowed to flow, which species is reduced? Okay, so this is number 19. 19. So the one that is reduced is at the cathode. The cathode is 1.506 volts. That's manganese. Which species is reduced? MnO4 minus is the species that's reduced. Right here. Okay? MnO4 minus. Actually, that's the species that's reduced. That's the element that is reduced. Okay, let's see. Same one, different question. What is the value of Q, the reaction quotient for this cell reaction? All right. So, this is 20. I think this is 20. In order to calculate the Q, we need the balanced equation. All right, so the anode, the oxidized side, is going to be the one with chromium, right? Because that's the one we flipped. So the oxidation step is going to be CR2072 minus plus 14, oops, not electrons, hydrogens, and 6 electrons yields, oops, I got that backwards, don't I? Sure do. We got to oxidize it. So we start off with 2 CR3 plus and 7 H2O. Now we get CR2072 minus and 14 hydrogens and 6 electrons. Okay. Then the reduction step is as written, MnO4 minus plus 8H plus 5 electrons yields Mn2 plus 4 waters, correct? Yeah. Okay. So now what we have to do is balance the electrons, right? These are the simplified reduction and oxidation steps, but we don't have a balance of electrons. So since that was 6 and this one's 5, the only way we can get there is cross multiply. So we have a 5 here and a 6 here. Okay, that makes this 10, 35, 5. Let's see. 5 times 4 is 20, and 2 and 70, and 30. Okay. That's 6 here, 48 there, 30 here, right? 30 electrons, that's good. 6, and 6 times 4 is 24. Right, now we can bring down a balanced equation. Let's see. I'm just going to start here. 10 CR3 plus 6 MnO4 minus plus 35 water plus 48 hydrogens. And the electrons are gone. Well, they don't come across. But if we have to calculate the actual voltage, then we want to remember that that 30 was there. Okay, now we have 5Cr2O7, 2 minus, 6 Mn, 2 plus, and I had water next, 24H2O, and then 70H plus. Okay, now we want to reconcile waters, 24 on that side. 24 from 35 is 11. And then hydrogens, 70 on that side. So 48 from 70 is 22, right? Okay. I don't see any way to reduce it further. Okay. So, Q. Q is going to be Cr2O7, 2 minus, to the 5th power, Mn, 2 plus, to the 6th power, and hydrogens to the 22nd power. This is a perfect illustration why we don't, for K and Q values, we don't include units of measure, because that would be a monster to represent. Okay, did I get everybody? 6. Yep. Now the denominator, Cr3 plus to the 10th power, and MnO4 minus to the 6th power. And then we don't include water, because water is a pure liquid. So that's it. Now we have to do is put the values in. Okay. Cr2O7 is 0.3 molar to the 5th power. Mn2 plus is 0.2 molar to the 6th power. And H plus is 0.01 molar. 0.01 molar to the 22nd power. Okay. Cr3 plus is 0.4 molar to the 10th power. And manganate ion is 0.1, 0.1 molar to the 6th power. Now all we have to do is be sure we don't mess up with the calculation. Close that cap. Okay. 0.3. 0.3, enter 5. There. So I get 2.43 times 10 to the minus 3 times 0.2 to the 6th power, which is 6.4, 10 to the minus 5. I'm going to multiply those two together. And then 0.01 to the 22nd power. Multiply that one times. Okay. Let's do this so we can track problems if we have them. I'm going to put the numerator is 1.555 times 10 to the minus 51. Then we'll do the denominator. 0.4 to the 10th power, and then times 0.1 to the 6th power. This is 1.0486 times 10 to the minus 10. I'll divide that one into that one. And that gives me 1.48 times 10 to the minus 41. Rounded off, 1.5 times 10 to the minus 41. Let's see if I recorded that one correctly. Yeah, B. Okay. That's a lot of work for just one little number. One tiny little number. Now, let's see. Before I erase that, am I going to need that information? Stand for this. What is the stoichiometric coefficient of H plus? Stoichiometric coefficient of H plus. 22. There it is right there. 22. Yep, D. Okay. Let's see. Looks like we got more. What is the cell potential at 25 as read on the digital meter? Okay. Now we need the Nernst equation. And let's see, this was number 22. So 22 says we're going to use this equation. E0 minus 0.0591 over the moles of electrons times the log of Q. Okay. How many electrons did we have? We had 30 electrons. And E0 was, I forgot the value. Let's go back. Contents. Is that E0? Standard reduction potential. Yeah, that's C, 0.176 minus, and there's a constant, and this is 30, and this is the log of Q, 1.48 times 10 to the minus 41. Okay, so back to the calculator. See, I've already got 1.48 in there. It's not rounded off, so let me do that. 1.48 exponent minus 41. Okay. Take the log of that one. Then times 0.0591 and divided by 30. Okay, that's minus 0.08. Subtract that from 0.176. So I change the sign and 0.176. And so I get equals 0.256 volts. And it does, wait a minute. I'm not on the right problem. Cut back down to 22. Let's see, 22, 1, 2. Here we go. That should be 0.26. Yeah, rounded off 0.26. So by using that mixture of concentrations instead of the standards of 1 molar, we get a higher voltage. Okay. Now the cell, I don't know if we discussed this in class, but the cell, even at that high voltage, won't run as long as under standard conditions, because standard conditions give you very high molarities. You have lots of material to work with. So that standard potential will be good for much longer than this voltage. This is an intensive property. So that works out 0.256 for now, but it'll go away a lot quicker than 0.176 because the concentrations are a lot lower. You don't have as much material to work with. Okay, we'll skip a few and get down to number 30. Following has a potential 0.92 volts. Okay, I don't even have to put this one on the board. H2, Hg2 plus hydrogen yields 2H plus. Well, maybe I better put it on the board so I can talk about it more intelligently. And H2, this is aqueous, this is a gas, and 2H plus, and Hg2 plus. Okay. That's 0, that's plus. This is 2 plus each one, and this is 1 plus each one. All right, so you may recognize this as a reduction against the standard hydrogen electrode. So the hydrogen electrode should be an oxidation. It goes from 0 to 2 plus. Yes, it is an oxidation. So that would be, it would yield 2 electrons. Yeah. And then the reduction would be from Hg. Let's keep, that's not right. H2H plus. There we go. I was mixing up my equations. This is oxidation. 0 for this hydrogen, plus 1 for that hydrogen. So it had to lose 2 electrons. Now this 2Hg goes from that, this one, and we had to add electrons to this one to get to Hg2 plus with a 1 plus there. So each one of this, we just had to add 1 electron to each one of these mercuries to get from a 2 plus to a 1 plus. All right, so this is the reduction. This is the standard electrode, so its voltage is going to be 0. And what is mercury? Well, we had to look it up. Right? If these concentrations are 1 molar and the pressure of hydrogen is 1 atmosphere, that's standard conditions. So we have to go down and actually look at the value for, for mercury. Hg2 plus, Hg2 plus. Here it is, Hg2 plus, 2 electrons. Wait a minute. Oh, that's right, 2 mercuries. That's right. 0.91. 0.91. All right. So this is written as an oxidation. This was written as a reduction. That's the answer. 30. There we go. That would be D. Of course, if you recognize this, if you recognize the standard hydrogen electrode, then you would know all you had to look up was this value, and that's your answer. But I spread it out like this just to make the point. All right, who's next? Let's see. Mark, who's next? Skipped a few. Now, if any of these are a problem to you, we'll stop and deal with them. But there is a lot of repetition in these problems. Okay, 44. 44. An excess of finely divided iron is stirred up in a solution that contains copper, and the system is allowed to come to equilibrium. That's the key, equilibrium. The solid materials are then filtered off and electrodes of solid copper and solid iron are inserted into the remaining solution. What potential develops? Because we're at equilibrium. The standard potential, E0, right, would be something. But E equals 0 because equilibrium. That's the key word. Okay, 49. You make a cell with aluminum electrode in a solution of aluminum nitrate and a zinc electrode in zinc nitrate. If you could increase the concentration of aluminum, which of the following is true about the cell potential? Well, let's see. If we've got aluminum, if we do an aluminum reduction, and what's the other one? Zinc. We have to find out which one is the anode and which one's cathode so that we can write them correctly in the balanced equation. So I would go to the table, go to our standard reduction potentials, find out what those values are. And let's see, I guess I'll go down. Let's see here. Okay, so aluminum and zinc, It's not there. There's zinc, 0.76. Negative 0.76. Okay, and aluminum is minus 1.66. Okay, so which one is the anode, which one's cathode? Well, they're both negative, so we have to flip this one to positive to make the total. Right? So if we make that one positive and reverse directions here, and this is the anode, and this is the cathode. Okay, so that means this aluminum is going to be on this side when we write the equation. And this one's going to be here, see, 2 plus let's see. Well, in order to balance them, we need to multiply this one times 2. 6, 2. Multiply this one by 3. 3. That means this would be 2. This would be 3. 3. Okay. And then on this side, we would have, still would have the zinc metal. And then this one would be flipped on the other side. So that would be 2Al plus. Okay. Okay. Now we can answer the question. Number 49. Back over here. 49. Here we go. Okay. If you could increase the concentration of aluminum 3 plus, which of the following is true about the cell potential? It would have a given cell potential here of, let's see, standard potential. And to answer this question, we can work from standard potential. So it would be 0 and then 9. So 0.9 volts. If we wanted to increase the concentration of aluminum, what would that do to the balance, the equilibrium, the direction of movement? We increase this one, it's going to be driven back that direction, which would decrease the voltage. Okay, it would decrease the voltage. Right. Let's see who's next. Skip a few more. 56. How many moles of electrons are produced from a current of 14.4 amps in 3.20 hours? How many moles of electrons? Okay. It doesn't give us a stoichiometry to work with. It just asks us how many moles of electrons are moving. So if we have 14.4 amps, what does that mean? That means coulombs per second. Okay. And we're working for 3.20 hours. Right? So those units don't match. What we need is to convert hours to seconds. Right? So how many seconds in an hour? Or you could do, right? You could get rid of hours with minutes, right? We know that's 60. And you could get rid of minutes with 60. There we go. Hours is gone, minutes is gone. Now we've got seconds, right? So seconds is gone. That leaves us with coulombs. Now we need to convert coulombs to moles of electrons. That's this one. 96,485 coulombs in the denominator. Per mole of electrons. Now we've got the units we want. Moles of electrons. Just have to crunch some numbers. Okay, times 3.2 times 3,600 and divided by 96,485. So that's 3 significant figures, 1.72 moles of electrons. Okay? And it takes you way back to the first semester. Dimensional analysis. All right. Let's see. Here we go. There's another one. 64. See, I need it. different marker. What mass of chromium could be deposited by electrolysis of an aqueous solution of chromium sulfate for 145 minutes using a constant current of 11 amps? Okay, this one goes a little bit further. So in order to, we need to know the stoichiometry. So sulfate is a spectator ion. We're really only interested in the chromate, in the chromium. So what's the chromium? Well, let's see. If we have Cr2 and SO4, 3, then this is 2 minus. That means 6 no. Sulfur. Excuse me. 2 minus means 6 minus. Yeah, 2 minus is the total charge on that. So that's a total of 6 minuses. That means plus 6. This is a plus 3. Okay. So we have chromium 3 plus 3 electrons yields chromium metal. That's our stoichiometry. We won't need that right now. What we have to do is find out how many moles of electrons are moving first. So we have 11 amps to start with. 11 coulombs per second. 11 amps. Then we're going for how long? 145 minutes. That has to be converted to seconds. So we have minutes, seconds. There we go, like that. And that cancels that. Now we want to convert coulombs to moles of electrons. So we have coulombs here, moles, electrons here. That's 96,485. Right? I get rid of coulombs. Now we have moles of electrons. Now the ratio is for every 3 moles of electrons, we get 1 mole of chromium. Okay. So that'll give us moles of chromium. And I'm not gonna add a step to this one. Let's get moles of chromium first. 60, 96,485, and 3. So this is 0.3306 moles of chromium. Now we can convert that to mass. We just need molar mass of chromium. We go to our periodic table. 52, rounded off, 52.00. Which is 3 significant figures. 17.2 grams, 17.2 grams. Okay. So the difference between this one and the last one was that we went a step beyond. We had to use stoichiometry to finish the answer to that question. Let's see, we'll skip a few. Oh, short answer. Okay. All righty. This is number 72. Balance the following equation. Didn't we do this one already? Didn't one like it. Yeah, I think we did one like this already. Well, we can do it again. That's no big deal. Cr2O7 2 minus, dichromate. plus iodine. Yeah, I know we did this one before. And we want this one in acidic solution. So -1 oxidation state, 3 plus oxidation state, minus and -5, +5 oxidation state there. We've done this one before. This is +6. Okay, so oxidation step, reduction step. Oxidation. We've gone from minus to +5. That's oxidation. Okay. Reduction. +6 to +3. By the way, when you're looking at toxicology reports for chromium toxicity, this is the bad one. This is bad, but not as bad. This is the really, really bad one. Okay. Let's see. Now we want to balance 1 iodine, 2 chromiums. There. Oxygens. 3 oxygens on this side. 6 hydrogens over here. And this one has 7 oxygens. 7 H2O. Maybe we didn't do this one. And 14 hydrogens. Now, oxidation. We're going to lose how many? Well, go from -1 to +5 is loss of 6 electrons for each iodine, and we'll only have 1 of them. For this one, we go from +6 to +3, so we have to add. We have to add 3 electrons for each chromium, but there are 2 of them, so that's 6 electrons. Oh, okay. I'm on track. So we don't have to balance the electrons now, we just have to bring it down. Right? That goes out. That goes out. And we get, let's see, CR2072 minus. Well, let's simplify things. 3 waters here, 7 there, that means 4 waters left over. Hydrogens, 6 there, that means 8 left over. So now we have iodine, 8 hydrogens, 2 Cr3 plus, and IO3 minus, and then waters, 4 H2O. And it looks like it agrees with the answer key. Okay, next, I got another one. We want this one in basic solution. Okay, so we're starting off with bismuth hydroxide. Let's see, 75. And SNO2, 2 minus, yields elemental bismuth and SNO3, 2 minus. Okay, so we're going to balance it. Yeah, we'll have to balance it acidic first. Okay. Oxygen and hydrogen are spectators. What we're seeing is a difference in oxidation states for tin and bismuth. That's 0. So this is, if this is 3 minus, this must be plus 3. This is minus 4, hold out 2, minus 2. This is plus 2. And this one is minus 6, minus 4 is plus 4. Okay. So now, oxidation step, reduction step. Who was oxidized? Who lost electrons? Tin went from 2 plus to 4 plus. Okay. And that means bismuth was reduced. Here and there. Okay, so 1 bismuth, 1 bismuth, 1 tin, 1 tin, we're good there. Oxygens. We need 1 more oxygen on this side. Right? That means we have 2 hydrogens on this side. Let's see. We have 3 oxygens here. We need 3 oxygens on this side. That means we need 6 hydrogens over here. Now for the electrons. We went from plus 2 to plus 4, which means we lost 2 electrons for each tin. And on this side, we gained 3 electrons for each bismuth. Okay? So 3 electrons, 2 electrons, cross multiply. All right, this is 3, 3, 6, 3, and 6. This is 2, 12, 6, that's good, 2, and 6. Okay. We might as well bring everything down first. Electrons are gone. We have 2 bismuth hydroxide. Then we have 3 SNO2, 2 minus. Then we have 3 waters, and we have 12 hydrogens. On this side, we have 2 bismuth and 3 SNO3 minus. Then we have water, 6 water, and hydrogen, 6 hydrogens. All right. Before we neutralize the hydrogens, let's deal with, well, actually, no, let's neutralize the hydrogens first. We got to incorporate these hydroxyls also because they make the situation more basic. So we've got 6 hydrogens there. Now we have 6 hydrogens here. Let's do the waters. 3 waters, 3 waters. Okay, neutralize the hydrogens. So plus 6 hydroxyls yields 6 waters and plus 6 hydroxyls. Okay, 3 waters over here, 6 there, that makes 3 here. Okay, now we've got 6 hydroxyls on that side. We've got 6 hydroxyls on this side. How'd that happen? Because that answer says we don't have any. Oh, I see what happened. You know what? Back up. I want to back up and take another stab at this one. That's 12. This is 3 waters. 12 hydrogens. 12 hydrogens, 3 waters, 2 bismuth. Okay, that's good. On this side, we have 2 of these, 3 of those. We have 6 waters. I see what happened. 6 waters and 6 hydrogens, right? 6 hydrogens. Okay. We don't have to add hydroxyls. Here's why we don't have to add hydroxyls. We have 6 hydroxyls on this side. And we have 6 hydrogens on this side. Okay. So if we in the waters, we had 3 waters over here. Now we have 3 on this side. Okay. 3 waters on that side. So what happened to the hydrogens? Hmm. 3 waters. We had 12 and 6, didn't we? Maybe I made a mistake up here. 3 hydrogens. 3 waters. It's 2. 3 times 3 is 6. Okay, that's right. Then when we combine them, 2 bismuth, 3 SNO2, 3 waters, 6 hydrogens. Wait a minute. That says 12. Okay, that's where I messed up. Yes, that's where I messed up. Why? Because we had 3 oxygens here, right? 3 oxygens there to make 3 waters. That makes 6 hydrogens, but I've already got 3 hydrogens. So I really only need 3H plus. That means 6 hydrogens here. That's the mistake. That should have been 6 here, and 6 those cancels those 6. And that leaves 3 waters, 2 bismuth, 3, yep. And this leaves SNO2, 2 minus, and 2. Okay. We don't have to do any neutralization because all the hydrogens are gone. That was my mistake right here. When I made that transition, balancing the waters and the hydrogens, I already had 3 hydrogens. I only needed 3 more. And then when we adjusted for the number of electrons, that balanced everything out. And it's still basic because of these hydroxyls. Right, so that's the correct answer. Your instructor just had to dance around the barn 3 or 4 times to get there. All right, is that the last one? Yep, that's the last one I have.